Hello all, welcome to GATE lecture video. So myself NITHYA, Assistant Professor, Department of Mathematics, S.A.E.C Engineering College. So today our topic is linear algebra. So today's content is definition of matrices, types of matrices, eigenvalues and eigenvectors, properties and problems. Definition of a matrix is, a matrix is a rectangular array, mn numbers arranged in n rows and n columns. So example, so it will be arranged in rows and columns, a11, a12, etc. ann, a21, a22, etc. a2n. Similarly, it goes on up to m rows, so am1, am2, etc. amn. So next, types of matrices. First one, row matrix. A matrix which has only one row, it denotes A equal to 1, 2, 3. So next is the column matrices. So matrices which has only one column is called column matrices. That is denoted as column wise 1, 2 or 3. A square matrix. A square matrix is a m and n which is equal, that is m rows and n columns is equal. So we have chosen here 1, 2, 3, 4, 5, 6 and 7, 8, 9. So 3 rows and 3 columns which denotes a square matrices. So next is a zero matrix. A matrix which has the elements will be, all the elements in the matrices will be equal to 0. So next is a diagonal matrix. A square matrix in which every element except the principal diagonal element is 0 is called diagonal element. So principal diagonal element is nothing but the main diagonal element 1, 2, 3. The remaining all elements will be equal to 0. We call that as a diagonal matrices. So next is a scalar matrix. A square matrix in which every diagonal elements are equal is called a scalar matrix. Example, so in the main diagonal element, all the element values will be equal. The remaining all elements will be equal to 0 is called a scalar matrix. So next is a unit matrix. So this is also same like a square matrix. A unit matrix is a square matrix made up of all elements except for the elements of the main diagonal element that are all ones. For example, so you have the 3 by 3 matrices here. So main diagonal elements will all be equal to 1. The remaining all elements will be equal to 0. So we call this as a unit matrix. So next is the transpose of a matrix. A matrix is obtained by interchanging the rows and columns of a matrix. So which is nothing but, if you are choosing a matrix A, that is 1, 2, 3, 4, 4, 5, 6, 7, 8, 9. If we change the rows to columns and columns to rows, we call that as a transpose of a matrix. So in transpose A, it is denoted as A part T. So 1, 4, 7, 2, 5, 8, 3, 6 and 9. So next is a symmetric matrices. So which is nothing but A is equal to A transpose is nothing but a symmetric matrices. If the transpose of a matrix is equal to itself, that matrix is called symmetric matrices. So A equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. If I choose the transpose of this matrix, this is also will be equal. So that is denoted as symmetric matrices. So next is the triangular matrices. So we have two types of triangular matrices here, which is upper triangular matrices and lower triangular matrices. So every element above or below the diagonal is 0. The matrix is said to be triangular matrices. So we call this as a upper triangular matrices. So next is the lower triangular matrices. So we have a 3 by 3 matrices here. So the lower diagonal elements alone it will exist. The remaining all elements will be equal to 0, which is nothing but here lower triangular matrices. So next is trace of a matrix. In a square matrix A, the sum of all diagonal element is called trace of matrix. So for example, so we have a matrices here 1, 5, 4, 3, 5, 6, 8, 1, 2. So trace is nothing but, so we have to choose the main diagonal element as a sum. So which is 1 plus 5 plus 2, so which is equal to 8. So similarly for a 2 by 2 matrices, the main diagonal elements are 1 and minus 3. So 1 minus 3 equal to minus 2. Next slide is eigenvalues and eigenvectors. That is the working rule for finding the eigenvalues and eigenvectors. So first step is we need to find the characteristic equation, determinant of A minus lambda equal to 0. So second, so we need to solve the characteristic equation to write the eigenvalues. So next is to find the eigenvectors. We need to choose A minus lambda into x equal to 0. So that is for different values of lambda. So this is your working rule for your eigenvalues. Note, corresponding to n distinct eigenvalues, we get n independent eigenvectors. That is, if the given matrices is a 3 by 3 matrices, so we have 3 eigenvalues and the corresponding eigenvectors are 3. So second one, if 2 or more eigenvalues are equal, so it may or may not be possible to get linearly independent eigenvectors corresponding to the repeated eigenvalues. So that is, if we have lambda equal to, for example, 2 comma 2 comma 3, so the 2 is repeated twice, so we call that as the algebraic multiplicity. So 2 is repeated 2 times. So algebraic multiplicity of eigenvalue lambda is the order of the eigenvalue as the root of the characteristic polynomial. So next one is the geometric multiplicity of lambda is the number of linearly independent eigenvectors corresponding to lambda. So next we see some properties of eigenvalues and eigenvectors. So we have the first property as sum of the eigenvalues of the matrix. So first one, sum of the eigenvalues of the matrices is the sum of the elements of the principal diagonal element. That is, we need to add the main diagonal element. Otherwise, we call it as a trace of a matrix. So next is product of the eigenvalues. So product of the eigenvalues is equal to the determinant of the matrices. So next is your second property. A second square matrix A and its transpose have the same eigenvalues. That is, if we have the lambda, that is the eigenvalues of A, the same eigenvalues will be the for A transpose. So next is your third property. The characteristic roots of a triangular matrix are just the diagonal elements of the matrices. That is, if we have the upper triangular matrices or the lower triangular matrices, the main diagonal elements is your eigenvalues. Property 4, if lambda is the eigenvalue of a matrix A, then 1 by lambda is the eigenvalue of the A inverse. So next to property 5, so if lambda 1, lambda 2, etc., lambda n are the eigenvalues of a matrix A, then A per m as the eigenvalues, lambda 1 per m, lambda 2 per m, etc. So then property 6, if lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also its eigenvalue. So next is property 7, the eigenvalues of a real symmetric matrices are real numbers. So next property 8, the eigenvalues corresponding to the distinct eigenvalues of a real symmetric matrices are orthogonal. So based on these properties, we are going to see the problems. Property 9, similarly, similar matrices are same eigenvalues. So next property 10, if a real symmetric matrix of order 2 has equal eigenvalues, then the matrix is a scalar matrices. So then two eigenvectors x1 x2 are orthogonal. So if the condition x1 transpose x2 is equal to 0. So next property 12, eigenvectors of a symmetric matrices corresponding to different eigenvalues are orthogonal. Next we see problem 1. So in problem 1, the sum and product of the eigenvalue of the matrices. So we have the matrix given. So we need to find the sum and product. So already we know by property. So sum of the eigenvalue is nothing but your trace of the matrices. So we need to write. So we need to add the trace. Trace is nothing but sum of the main diagonal element. So which is equal to minus 1, minus 1, minus 1, which is equal to minus 3. So this is nothing but sum of the eigenvalues. So next is we need to find the product of the eigenvalues. So product of the eigenvalues is equal to, so which is determinant of A. So we need to find the determinant of the given matrices. So which is minus 1 times of, so minus 1 into minus 1, which is 1, minus 1. So next to the second element will be in the matrices as minus of the value. So minus 1 times of minus 1 minus 1. So next to the third element is plus 1 times of 1 plus 1. So the result of this will, so minus 1 into minus 2, which is plus 2. So that is equal to 4. So the result here, sum of the eigenvalues is minus 3 and product of the eigenvalue is 4. So the answer for this is minus 3 and 4. So which is your second subdivision. Second problem, the product of the eigenvalue of the matrices is A equal to. So we have a 3 by 3 matrices here. S16 is given, then the third eigenvalue we need to find. Product of the eigenvalue equal to. So determinant of A, so this is your formula. So product of the eigenvalues we are choosing it as lambda 1, lambda 2, lambda 3 which is equal to determinant of A. So now the given condition is product of two eigenvalues is 16 is given, that is lambda 1 into lambda 2 given as 16 into lambda 3 which is equal to, so we need to find the determinant of the matrix. So that is 6 times of 9 minus 1. So plus 2 times of minus 6 plus 2. So plus 2 times of 2 minus 6. So that is equal to 6 times of 8 plus 2 times of minus 4 plus 2 times of minus 4. So you have 48 minus 8 which is equal to 32. So we found 16 into lambda 3 equal to 32. So next from this lambda 3 is equal to, so 32 divided by 16 which is equal to 2. So now the third eigenvalue here is lambda 3 equal to 2. So which is your solution. Third problem, so two of the eigenvalues of the matrix given here 6 minus 2 2, minus 2 3 minus 1 2 minus 1 and 3 are 2 and 3, that is two of the eigenvalues is given. So for 3 by 3 matrices we have 3 eigenvalues. So lambda 1 equal to 2 and lambda 2 equal to 8 is given. So we need to find the third eigenvalue. Same like previous problem. In previous problem we have chosen the formula product. Here we are going to choose the sum. So now here sum of the eigenvalues is equal to, sum of the eigenvalue equal to trace of the matrix so trace of the matrix A, this is your condition. So sum of the eigenvalues we are denoting it as lambda 1 plus lambda 2 plus lambda 3 equal to trace of the matrix in the given as 6 plus 3 plus 3. So now first two eigenvalues are given, so which is 2 and 8. So 2 plus 8 plus lambda 3 which is equal to 12. So here lambda 3 equal to 12 minus 10. So that is equal to 2. So now the third eigenvalue result is 2. So lambda 3 equal to 2. Is our fourth problem. If 3 and 15 are two eigenvalues of A, so then determinant of A without expanding the determinant. So that is we need to find the third eigenvalue without expanding the determinant we need to find. So first choose your given data. So lambda 1 equal to 3. So lambda 2 equal to 15 is given. So now we need to find the third eigenvalue which is lambda 3. So first to choose sum of the eigenvalue formula. So sum of the eigenvalue equal to, so trace of the matrix. So trace of the given matrix A. So now the sum of the eigenvalues is 3 plus 15. Plus the third eigenvalue we are denoting it as lambda 3, so which is equal to trace of the matrix 8 plus 7 plus 3 which is equal to, this one right side is 18 and the left side is 18 plus lambda 3, so lambda 3 equal to 0. So after finding the three eigenvalues, so now choose the formula for product. So product of the eigenvalue equal to, so which is determinant of the matrix A. So without expanding the determinant we need to find. So choose your eigenvalues as a product. So lambda 1 into lambda 2 equal to into lambda 3 equal to determinant of A. So we have the values here 3 as a first eigenvalue. So next is 15, and the third eigenvalue we found it as 0. So which is equal to determinant of A. So from this we brought the result. So determinant of A equal to 0. So that is first option. Next problem, if 2, 2, 3 are the eigenvalues of the given matrix A, so then the eigenvalues of A transpose are. So already we have seen some properties. So in that, if lambda are the eigenvalues of A, then lambda is the eigenvalue of A transpose also. 1 equal to 2, lambda 2 equal to 2, and lambda 3 equal to 3 is given. So the same is here, the eigenvalues of the A transpose. So which means the first option 2, 2, 3. So next is the eigenvalue of the matrix A equal to. So we need to find the eigenvalue of the given matrix. So the A matrix is 2, 1, 0, 0, 2, 1, 0, 0, 2, which is like upper triangular matrices. So upper triangular matrices is nothing but the main diagonal element is your eigenvalues. That is, we need to choose 2, 2, 2. So which is your first option. So next is problem number 7. So if A is a 5 by 5 matrices, so if A is a 5 by 5 matrices with a trace 15, and if 2 and 3 are eigenvalues of A, so each with algebraic multiplicity 2, so then the determinant of A is equal to. So I have to choose the lambda first. So lambda 1 equal to 2. So and 2 is repeated 2 times, which denotes lambda 2 is also equal to 2. So lambda 3 equal to 3. So 3 is also again repeated. So lambda 4 equal to 3. So now we need to find what is your lambda 5. So that is your fifth eigenvalue. So now the trace is 15 is given. That is 5 by 5 matrices, trace is 15 is given. So choose the formula, sum of the eigenvalue equal to. Sum of the eigenvalue equal to, so trace of the matrix, so trace of A. So which is lambda 1 plus lambda 2 plus lambda 3 up to lambda 5. So that is equal to trace of the matrix given is 15. So now add all the data here. So 2 plus 2, 3 plus 3 plus lambda 5. So equal to 15 is given. So lambda 5 equal to 15 minus 10, which is equal to 5. So now we found, so lambda 5 equal to 5. So next we need to find the determinant of the matrix A. So now, so product of eigenvalue equal to, so determinant of A. So the 5 eigenvalues we need to multiply. So the eigenvalues are, so 2 repeated twice, so I am writing it as 2 square. Then 3 is repeated twice, so 3 square. Then the fifth eigenvalue is 5, so which is equal to determinant of A. So now the solution for this is determinant of A equal to, so 180. So which is your fourth option. This is your eighth problem. So 2 of the eigenvalues A equal to, so now the matrix given is 3 minus 1 1, minus 1 5 minus 1, 1 minus 1 and 3 are 3 and 6. That is 2 of the eigenvalues is given, 3 and 6. Then the eigenvalue of A inverse we need to find. So now we already know the property. So lambda is the eigenvalue of A means 1 by lambda is the eigenvalue of A inverse. So using that property, so we need to find the lambda first. So now 2 of the eigenvalue given is lambda 1 equal to 3 is given. So lambda 2 equal to 6 is given. So we need to find the third eigenvalue. So now choose the sum of the eigenvalue property. So sum of the eigenvalue equal to, so which is trace of the matrix, 3 plus 6 plus lambda 3, so which is equal to, so trace of the matrix here is 3 plus 5 plus 3, so 9 plus lambda 3 equal to 11. So lambda 3 equal to 11 minus 9, which is equal to 2. So we found the third eigenvalue, that is equal to 2. So now the eigenvalues are, so lambda equal to 3, 6, 2. So this is all the eigenvalues for the matrix A. So next we need to find the eigenvalues for A inverse. 1 by lambda is the eigenvalue of A inverse. So which is 1 by 3, 1 by 6 and 1 by 2. So this is your solution. So where it is, the first option is 1 by 2, 1 by 3 and 1 by 6. So now the next problem. So for what value of x will the given matrix become singular? So we have the condition here for the singular matrices, determinant of A equal to 0. So for the given matrices, we have to choose determinant of A equal to 0. Singular matrices condition is determinant of A equal to 0. So now choose the determinant for the given matrices. So 8 times of, so 0 minus 12. So minus x times of, so 4 into 0 is 0 minus 24 and the last value is 0 we are having. 0 multiple of anything will be 0, which is equal to 0. So now 9 to 6 plus 24x equal to 0. So 24x equal to 9 to 6, so x equal to 4. So this is the value for x equal to 4. So now the next problem, for the matrix A equal to 4, 1, 1, 4, the eigenvalues are. So now, so the given matrices is a 2 by 2 matrices, so we need to find the eigenvalues. So we are choosing the characteristic equation here. So determinant of A minus lambda equal to 0. So using this condition, we are finding the eigenvalues. So determinant of the first matrix A is 4, 1, 1, 4. So minus lambda times of the identity matrix of a 2 by 2. So 1, 0, 0, 1. So which is equal to 0. So now subtract the corresponding terms. So 4 minus lambda into 1. So next 1 minus 0, next 1 minus 0 again, so 4 minus lambda, so which is equal to 0. So now the matrix multiplication, so 4 minus lambda the whole square minus 1 equal to 0. So now solve this, so 4 minus lambda the whole square, which is 16 minus 8 lambda, so plus lambda square minus 1 equal to 0. So now this brings lambda square minus 8 lambda, so plus 15 equal to 0. So factorize this equation. So factors for 15 are, so lambda minus 5, lambda minus 3 equal to 0. So from this lambda equal to 3, 5. So these are the eigenvalues of the given matrices, so which is 3 and 5. So next is 11th problem. Let A be a 4 by 4 matrices such that minus 1, 1, 1, minus 2 are its eigenvalues. If B equal to A power 4 minus 5A square plus 5I, then we need to find the trace of A plus B equals. So now the eigenvalues of a 4 by 4 matrices is given. So that is lambda equal to minus 1. So lambda equal to minus 1, 1, 1 and minus 2 is given. So this is your eigenvalues of the 4 by 4 matrices. So now we have the matrix B equal to A power 4 minus 5A square plus 5 into I. So this is all the eigenvalues of the given matrix A means. So what is your A square? So we need to square the corresponding eigenvalues. So minus 1 square is 1, 1 square is 1, 1 square is 1, minus 2 square is 4. So this is your A square eigenvalues. So next we need to find A power 4. So A power 4 is nothing but again square the A square eigenvalues. So which is 1, 1, 1, 16. So this is all the eigenvalues for A power 4. So now substitute in B. So B equal to, so 1 comma 1 comma 1 comma 16. So minus 5 times of A square eigenvalues. So that is 1, 1, 1 and 4 plus 5 times of the identity matrix, which is 1, 1, 1, 1. So now we need to subtract the data here. So 1 minus 5, so plus 5, which is 1. So this is your first data. So second data is 1 minus 5 plus 5. So again 1, then 1 minus 5 plus 5. The last one is 16 minus 20 plus 5. Okay, so now choose your eigenvalues for B matrices. So that is 1 comma 1 comma 1. Which is 1. So now after finding this B, so we need to find the trace of the matrix A plus B. So trace of A plus B as, so first A matrix and B matrices traces are, so minus 1 plus 1 is 0. So next one 1 plus 1 is 2. So next value is also 1 plus 1 is 2. The last value is minus 2 plus 1, which is minus 1. So now the trace nothing but sum of the values. So 0 plus 2 plus 2 minus 1, which is equal to 3. So now this is the solution for this problem. So 3 is the trace of A plus B. So next is 12th problem. The trace of the matrices, the matrix given is power 20, that is 2 1 0 0 2 0 0 0 3. So power 20 it is given. So first we need to analyze what type of matrix is given. So this is a upper triangular matrices. The main diagonal element is your eigenvalues, that is lambda equal to, so 2 comma 2 comma 3 is your eigenvalues. So now the power 20 is given. So 2 power 20, 2 power 20 and 3 power 20. So we have the solution. Actually we need to find here is trace of the matrices, that is trace of the matrix A. So that is the given matrices, we are denoting it as A. So 2 power 20, so plus 2 power 20 plus 3 power 20. So 2 times of 2 power 20 plus 3 power 20. So that is your third option is your solution. So next is, if A equal to 3 minus 2, 2 minus 1 is given, so that is a 2 by 2 matrices, then A power 20 equals. So we need to find A power 20. So this will be, so we are going to do it in a short way. So A equal to 3 minus 2, 2 minus 1 it is given. So first add the corresponding row elements. So 3 minus 2, 2 minus 1 is given. So when I add these two, I am getting the result as 1, and here also I am getting the result as 1. So now go for your options. In the options, wherever you are getting the same result, that is your option. So first option, when I add these two, I am not getting 1. Second option, I am getting it as 1, but here also I am getting it as 1. So and in the fourth option, when I add these two, I am getting 1 as a result, and here I am not getting equal to 1. So and here when I add, this is not equal to 1. So therefore only second option, when I add the elements in the row wise, so 41 minus 40 it is 1, so 40 minus 39 it is 1. So this is your right option. So next, find the eigenvalues of adjoint of the matrix A if A equal to, the matrices is given. So we need to find the adjoint of the matrix. We know A inverse equal to 1 by determinant of A into adjoint of A. So this is your formula. So using this formula, we are going to find the eigenvalues of adjoint of A. So adjoint of A can be written as A inverse into determinant of A. So A inverse into determinant of A. So first we need to find the eigenvalues of A inverse, and determinant of A. Already we know how to find determinant of A, that is product of the eigenvalues is nothing but determinant of A. So first is we are finding the lambda, so that is lambda equal to, since the given matrices is upper triangular matrices, the main diagonal element is your eigenvalues, so lambda equal to 3, 4, 1. So since this is the eigenvalues of A, so what is your inverse? That is 1 by lambda. So 1 by 3, 1 by 4, next 1. So this we need to find the product. So product of the eigenvalues. So product of eigenvalue equal to, so determinant of A. So product is, so lambda 1, lambda 2, lambda 3 equal to determinant of K. So we have the lambda, that is 3, 4 and 1 here. So 3, 4 into 1, which is equal to determinant of A. So implies determinant of A equal to 12. So now we found what is the eigenvalues of inverse and determinant of A. So now substitute in the formula. So adjoint of A equal to, so adjoint of A equal to A inverse times of determinant of A. So A inverse is 1 by 3, 1 by 4 and 1 into determinant of A is 12. So when I multiply with each eigenvalues, so I will be getting 4, 3, 12. So this is the solution for the adjoint of A matrices. So that's all we have completed. Next session in the linear algebra and the corresponding topics. Thank you.